Good afternoon, everyone. I am Sachin. I will be TA for the course Basics of Finite Element Analysis 2 for this term. I will take the tutorial sessions weekly, Saturday 3 to 5 p.m. I will briefly every weekend I will briefly explain again the topics of the FEA happened in that course, and then solve some tutorial problems. We can discuss if you have any doubts regarding those problems or the lessons. This is the first tutorial session and first week of the course. In this week, in the course, the overview of the whole course is explained, and then it's the part 2 of Basics of Finite Element Analysis. uh, Sorry, increase volume. Is it better now? Okay. uh, so in this week, mainly the basics of finite element methods, like 1D problem with one variable problems, how to solve using FEA has been revised, which were part of the FEA 1. In that, mainly the procedure would be, I'll just write the main points. General procedure using FEM. First will be to discretize the domain. Like for any problem, you will be given the governing differential equation and the domain on which it is acting and the boundary conditions that are applicable to the problem. So initial first step is to take the domain and discretize into elements. Second step is to, oh sorry, I didn't share the screen. Let me share it. Yeah, now you can see the screen. So for any problem, first you need to take the yeah. Sorry. First, you will discretize the domain into elements. Second, for each element, you will choose the interpolation function. These interpolation functions could be like linear function or quadratic function or third order linear polynomial. Depends on the problem and choice. Third part is to write the weak form of the equations. This one you can do it by like multiplying the error with the weight functions. With weight functions, and then you can use UV integration rule to reduce the order of derivative. By using UV integration rule and reducing the order, the order of the interpolation function which is needed to solve the equation is reduced, we can use simpler interpolation functions and still solve the problem. Once you have the weak form interpolation functions ready, for each element you will find the stiffness matrices, and then you assembly the matrix like stiffness matrices of all elements. Once assembly is done, it still we cannot be solve this equation because the stiffness matrix will be similar. We need to apply the boundary conditions in order to like if once you apply boundary conditions, then only the stiffness matrix can be invertible. Apply boundary conditions, and then finally you can solve for the uh, solution. It's just inversion. So this is the standard FEM procedure steps for any kind of problem. In this week, professor has showed you for one-dimensional problem with one degree of freedom. He has shown for the bar problem, which is like 1D bar problem, and the degree of freedom is the displacement along the x direction. And as any numerical method, this is also an gives an approximate solution, and to find the error between the original solution and approximation solution, you typically uh, like take the numerical solution and compare with analytical solution, and then find out the error and then use it. And the error also depends on error depends on the number of elements you have chosen. Like as you increase the number of elements, the error decreases. And then as you and also the order and choice of interpolation functions. Generally speaking, as you take the higher order functions, it will give less and less error, and also it depends on the uh, translation error of the system, like basically the error due to computational like the CPU. So this is the basic overview of the concepts happened in this view. If you have any like doubts in these like videos, you can ask now, then we can proceed to solve one simple example problem. Yes, Shivan.
So actually, I want to ask like for interpolation function, if we are
Yes.
assuming it to be like a plus bx, then it is told
Yes.
that there are two functions. One is constant one and another is x. So
Yes.
these two are interpolation functions, one and x,
Uh,
right?
no. Uh, it's 1 plus x is the interpolation function. It's not 1 and x.
Uh,
Your question is like for there are two videos. In the initial videos, professor has stated an interpolation function as a plus bx, and then he solved the problem. In the later videos, he chose u as ui psi I. That's something like u1
Yeah.
psi 1 plus u2 psi 2, right?
Yeah.
So this complete psi 1 and psi 2, uh, it actually it's very much similar to this one. Here we are using directly like we are taking arbitrary linear function a and a plus bx. Here a and b are unknown coefficients. If you want to write them in terms of u1 u2, you will end up with this. I will let me just show you one simple like how it uh, comes. So if like same example we will take like this is one element, and its element is from 0 to L, and let's say we took the interpolation functions as a plus bx. This is the interpolation function. Fine. Then this is first node and this is second node, and if you want to have the like u1 like solution at first node, you will have a plus b u1, right? Sorry. One second. So like at x is equal to 0, u will be u1. So if you substitute, you will get a as u1, and at x is equal to L, u is u2. That is, you will get a plus bl is u2. It's nothing but that is 1 b is u2 minus 1 by L, u2 minus u1. So if you take the interpolation function and write it in terms of like substitute this a and b into that one. Here interpolation function is a plus bx, and a is u1 and b is 1 by L n times u2 minus u1 of x. Then you will have it as u1 times 1 minus x by L plus u2 times x by L. So here in both the cases the interpolation function is a plus bx, but we are just rewriting the interpolation function in terms of the degrees of freedom so that we can directly solve for u1 and u2 directly, which makes much more sense because it directly gives the information of the solution on the nodes. So we call this as shape functions, where we get 1 minus x by L and x by L. These are called shape functions. It's just that we are rewriting the interpolation in terms of the degrees of freedom at the corresponding nodes. Is it clear now?
But it is also told that the variation of the unknown variable is summation of interpolation functions. So
A variation of unknown variables is. Sorry, could you repeat once again?
like Like if a known variable is temperature, then
Yes.
and we are assuming it something, so it is summation of interpolation functions.
Uh, uh, you mean like, is it? Are you talking about this one only, or
Yeah, it is,
any
but
different?
it is a summation. So it is a summation of different i's.
Yes. Here, as you can see, we have u1. This is one, and then summation certain part. Like
Okay.
you did it right. Like
But then save function or interpolation will be 1 minus x by L and x by L,
yes,
not a
yes.
plus bx. That but that
It's
is
just about context wise. It just changes. Here, interpolation function is a plus bx, but we are just rewriting it in different format. That's it. So still, you can proceed by taking, just you can take it, u is equal to a plus bx, and then you can just proceed to solve the whole solution, like just using this as well. Then you finally, the unknowns will be a and b for you, and like you will get something like a times a b is equal to f. You can solve it for a comma b. Then if you substitute them, you can finally get again u. It's fine. But when you solve for a and b, you generally it doesn't do much meaning, doesn't have direct meaning. And when you convert it into terms of nodal degrees of freedom, you will directly know that u1 and u2 are the solution at nodes 1 and 2. That is why like this is converted in terms of shape functions. So the interpolation function is still linear. You can just observe that here a plus b x is linear polynomial, and even this one is a linear polynomial.
so basically we have one interpolation function. We are breaking it into two interpolation
Yes,
functions.
yes, basically yes. It's the yeah, true. We are just rewriting it in terms of nodal solutions. You can
Okay.
still think, and we don't call this 1 minus h by l and h by l as interpolation functions. We call it shape functions. And
Shape function and interpolation functions are different.
yes, they are not the same. You will with interpolation function. Um, One second. Is it? I'm not sure about the terminology. I think he professor used interpolation function for this one, right?
Actually, he
They are a
said
bit,
both are same interpolation functions.
yeah, it's they are just, as I told you, they are same, just rewritten in different format. But when you want to have the solution with just one shape functions, it's not possible. Like in an element, you will have nodes, and depending on the number of nodes, you will have the same number of shape functions. And if you want to do the interpolation, it will be uh, nodal times the, like you need to take the summation of all the shape functions, then only you can get the final solution. It is still can be like seen as an interpolation function. You like not an individual shape function, but it's like summation of all the shape functions in that element. Like here, if you cannot just state 1 minus x by l and just say that 1 minus x by l times u1 is your solution at arbitrary point. This is wrong. You need to take like both the shape functions, and like u1 times x1 minus x by l plus u2 times x by l, then only this is the proper way of finding the solution at arbitrary point x. But when you take this one directly, it's directly u is equal to a plus bx. This one is the solution in the element. Slight differences, but ultimately like both are like same. We are just writing in a different format.
So as a whole also we say it as a interpolation function, and if we break it they are in smaller interpolation
No,
function.
no, no,
This is how we can
they are
quote
they
it.
are called shape functions. It's you can smaller interpolation function. It's not like that. Something like you can think of this as you have when you have a plus bx, it's like you have a coefficient. Sorry, like when you have your u as a plus bx, you can think of it as some arbitrary coefficient times the 1 and b times x. You can think of this as two independent functions and corresponding coefficients to scale them. Similarly, when you write this as u1 1 minus x by l plus u2 x by l, these are two functions and corresponding coefficients. Like instead of we are writing this in terms of 1 and x, we are writing in terms of 1 minus x by l and x by l. If you see these in differences, here you can call this 1 and x as the basis functions, and even here 1 minus x by l and x by l are same basis functions. So maybe you can think, yeah, it's, but you shouldn't compare this one with this one, right? You need to compare this one is equivalent to this one, like summation, and 1 and x are like something similar to this 1 minus x by l and x by l. So whenever you think of a plus bx, you need to think directly in terms of ui psi I. You shouldn't compare a plus bx with just psi. Is it fine?
Okay.
Like these a plus bx and ui psi a, these are both are equivalent.
Okay.
It's just slight differences are present when you call them as even shape functions are used for interpolation, but not just directly. You cannot use one shape function and use it for interpolation. You need to use the all the shape functions present in the element and then use it for interpolation. That's it.
Basically, what we have, you have derived this u1 1 minus x by l and plus u2
Yes.
from the
Yes.
same equation a plus b x.
Yes.
So they
Here.
are
Yeah.
equivalent somewhere.
Yeah, they are
So,
equivalent.
but
We start
here,
from a plus bx and then we arrive at this.
yeah, but at
Uh,
one, when we are considering a plus bx, the shape functions are 1 and x. And when we are taking
uh,
this one, the shape function are 1 minus x by l and x by l.
no, one more thing. Uh, Here you can one and x you basically call it as basis functions, not When you say shape functions, we indirectly we say that those shape functions should be multiplied by the like solution at the nodal points, like to get the interpolation. You get it right? Like when you have shape functions psi I, to get the whole solution you just multiply with the solution at the nodes, and then it's done. Then this like these are called shape functions. But this one and x you have, these things they are not multiplied by the u1 and u2 to get the solution. This is not correct. These are multiplied by a different
Yes, yes.
provisions. You get it right? So although these are
Yeah, yeah, yeah.
so these are called basis functions, like and even these are also called basis functions, but it's special. These specially which can be written in terms of u1 u2, they are called shape functions. So it's like basis functions is nothing but you have, you want to, like let's say you your solution is linear and you want to have the independent functions and then their linear combination to get the whole solution. Here like linear independent functions will be like 1 and x in this case, and their linear combination is a plus bx. This is one case, like one of the way to get the linear function, and this is another way of getting the like just different set of basis function. That's it. Like and many more are also possible. You can write it in a very much different way than these two as well. This one is like when you say a plus bx
Like
is
one.
straightforward to think in as a linear function, and when you write in this function it's very straightforward to think in terms of solutions at degrees of freedom.
But as in this case, A1 and BX,
Yes.
here as a whole, A plus BX is an interpolation function. But as a whole,
Yes.
U1 1 minus X by L, this whole also is an
Yeah.
interpolation function.
Yeah. This whole is an interpolation. Uh,
And 1 minus X by L and X by L are also interpolation functions.
yes.
Okay, okay, thank you. Thank you.
Yes. Like when you get this, then you can just substitute x in this, and then it's the solution. Yeah. it's it's fine. You can still think as this as an interpolation functions, but just you need to remember that it's you shouldn't just write this and then it's not the solution. You need to have both the shape functions. You get it? It's like let me show you how it works. If this is the first node and this is the second node, and you have, let's say, some solution here u1 and some solution here u2, then we want to have the linear interpolation. So something like we will have here corresponding to first node, something like this. It's like the effect of u1 in the whole domain will be linear, and at the time it goes to u2, u1 effect will be 0. Similarly u2 uh, will be something like this. So this one would be 1 minus x by l function, and this is x by l function. So it's this one interpolates u2 from here 0 to L, and this one interpolates u1 from 0 to L. But to get the whole solution u, which is a combination of both, you need to have summation of both. Still you can think of these things as an interpolation functions, but just you need to keep this in mind that you need to have the summation. Uh, uh, I hope it is at least somewhat better clear. You don't have to worry much about the terminology, but understand the concepts, like how and where these are coming from. You get it?
Thank you. Thank you.
Any other doubts other than this? Okay, then maybe we will solve one problem, like one bar problem using FEM method, and then just practice it. The problem is something like this. It's a some kind of bar, vertical bar, and then on top it's a distributed load of 20 kilonewton per meter square. It's acting, and the cross section area is varying, and width wise it's constant. Width is a constant value of 0.5 meters. Just breadth is varying from 0.5 at let's say x is equals to 0 to x, x is equals to 2 meters. Fine. And for a bar, the governing equation is, this is a standard bar equation, minus d by dx ea du by dx is equals to f. So this is the governing equation for this problem, and then and this is the problem. First, we want to solve it using like make it simplify the problem into 1D, and then we can probably use the FEM. So we can consider directly it as a 1D problem. But you need to keep in mind that area of this bar is changing with x, and then you need to know what are the boundary conditions are. So at the bottom you have, this is the fixed support, that is u is equals to 0, and at the top you have a force acting on it, which is 20 kilonewton per meter square. It's the distributed load, so effective force will be 20 times area of the top column, which is 20 times 0.25 is 5 kilonewton. That is acting on top. and bottom. So effectively right now you have the down differential equation that is acting. You have the domain which is running from x is equals to 0 to x is equals to 2. You have the domain defined. You have the boundary conditions defined. Boundary conditions are u is equals to 0 at x is equals to 2 meters, and force is equals to 5 kilonewton at x is equals to 0. So once you do this, the whole problem is well defined. You have differential equation ready. You have the, you know what is the domain right now, and you know what are the boundary conditions are. Is it clear till now? Okay. So once these things are ready, now we can use the steps defined mentioned in the course. We need to discretize the domain into elements. We for the like for simplicity and for calculation, we'll just divide the domain into just two elements. Let's say this is element 1 and element 2, and then once the elements are ready, you need to fix on the interpolation functions. We will first point, two elements we are dividing. Second one, we are using linear interpolation function. That is, u will be u1 psi1 plus u2 psi2. Uh, which is psi1 and psi2 are nothing but 1 minus h by l and h by l. This is for a generalized element, like you can call general element or local coordinate system, which starts from x is equals to 0 to l for an element. This will be the solution and how the interpolation will be. Then you need to write the differential equation in terms of in the integral form. Differential equation is minus d by dx. Here we need to take e is fine, but we need to take care that area is a function of x. We cannot just directly bring it out. So for this we multiply the error with the weight residual function. So in this case, error is nothing but minus d by dx ea du by dx minus f. This is the error, and then you are multiplying it with the weight function and then integrating it over whole domain. That is 0 to 2. And if we use this directly, we have second order derivative on u, so we need to use at least quadratic shape functions. To avoid that, we uh, generally go for weak formulation, like weak form, that is we use uv integration rule and then um, modify the problem. It's uv integration rule is something like uh, we'll just take the first form, d by dx, first term, d by dx times a du by dx times w dx. This it's like this derivative will shift to this one. It will become ea of x du by dx dw by dx, and there will be minus, and then second term would be a boundary terms, and then it's like 0 to L. Here we are integrating over one element. Later we need to do this for all the elements and then do make the assembly. So for one element in local coordinates it's like 0 to L. I am just writing 0 to L everywhere. So, and you can just batch substitute them into the original equation, which will be E A of x du by dx dw by dx. This will be the first term, and second term is dA of x du by dx w 0 to L, and then the final term f times w dx is equals to 0. So this is your weak form. U is your primary degree of freedom, that is the displacement in this problem. W is your weight function. F okay, let's maybe I should use different notation. I will use this as speeds. Don't confuse this F and this F. Let's take the top load as P. Yeah. So now you have this one ready. You can just substitute your functions in this and then solve it. Before that, we'll just find out what A of x is. A at x is equals to 0, A is equals to 0.5 times width 0.5. At x is equals to 2, A is equals to 1.5 times 0.5, and it is varying linearly. So you can just take A as it is varying linearly. A plus bx area you can take. Then you can straightforward, if you substitute x is equal to 0, here you will get A as 0.25, and then here A plus b times 2 is 1.5 times 0.5, 0.75. So B will be 0.75 minus 0.25 by 2, 1 by 4. A is also 1 by 4. Sorry, it's very messy, but you will have the area of it as A is 1 by 4 plus B 1 by 4 x. 1 by 4 times 1 plus x. This is your area variation along with x. And you have u of x as in terms of shape functions, this one. And then the weight function w. We will slowly start substituting them and then is it clear till here? Any doubts till this point? I'll just reverse. This is the problem. We have simplified it into 1D, and then we have the bar governing differential equation, and we found out that the boundary conditions are u0 at bottom and force 5 kilonewton at top. And then we found the area variation in terms of its, which is 1 by 4 times 1 plus x. And then we are using linear interpolation functions, that is u of x will be u1 times 1 minus x by l plus u2 times 1 x by l. And then we took the differential equation and then converted into integral by multiplying the weight function to the error, and then made into weak form, and the order of derivative is reduced. Now we are going to substitute all the equations into this. So it will be, and keep note that we are doing this whole integral just for one element, and we are right now dealing with the local coordinate system of the element, which is from 0 to l. Then later, while we doing assembly, we can use the uh, use it for two elements and then see how it goes. So E times is 1 by 4 1 plus x du by dx u1 times minus 1 by l plus u2 times 1 by l. This is the derivative, minus 1 by l u1 plus 1 by l u2. And then we have w, which weight function, which we take it same as the shape functions. So that is, you need to do it for w is equals to psi 1 once, and then w is equals to psi 2 another time. So in this way, for these two cases you need to do, and you will get two equations. So for w is equals to psi 1, dw by dx will be minus 1 by l dx. And keep in mind that this F is the body force which is acting through the whole body, and in this problem we don't have any body force, so F is 0 in this case. So we can completely neglect this term and make it to 0. And then we have this still we have this term du by dx and psi 1 0 to L is equals to 0. For W is equals to psi 1. Similarly, we will solve for W is equals to psi 2. Then we will have 0 to L E times 1 by 4 times 1 plus x. It's du by dx will not change, and dw by dx will be 1 by L times dx. And let's keep this as it is for now. So here we can segregate these terms, or else we can solve them. Okay, we will write in terms of u1 and u2. We want to segregate these things because right now the unknowns are u1 and u2. So this part will be we will get a stiffness matrix with 4 terms, and first part this part will go as the first term, and this part and we have minus 1 by L outside. This is your first element. Then we will have this second part, I will just simplify it and write so that it's easy to understand. This will be the first equation, this will be the second equation. First will be E times 1 by 4 1 plus x minus 1 by times L 1 by L square dx times u1 plus integral 0 to L E times 1 by 4 times 1 plus x 1 by L times minus 1 by L. This times u2 is equals to 1. Okay, And the second equation, similarly, it would be E times 1 by 4, 1 by h, and then 1 by L. 1 by L will be 1 by L square times dx times u2. Okay, this is minus 1 by L square. So now you can clearly see this in terms of u1 and u2. First part, second part of stiffness matrix, third part and fourth part. These things we can write it in matrix form as K11, K12, K21, K22 times U1, U2. Here you can, this will be your K11 and this is K12, K21, K22. So you have multiplied K11 times U1 plus K12 times U2 is equals to right hand side F1, F2. This one will be your F1, this will be your F2. So this is your how your stiffness matrix will look like for one element. One element. I will just revise the problem once again. What uh, we have we have been doing till now. So this is our problem statement where we have a bar problem with a load acting on top and then fixed at bottom. We have the bar governing equation, this one, and then then we want to solve it using FEM. First thing which we did is to simplify the problem to 1D, uh, where bottom its boundary condition will be used 0 and top force is 5 kilonewton, and then area is a function of x, which we found it as 1 by 4 times 1 plus x. Then we start the FEM procedure by, we have assumed we discretize the domain into two elements, two equal elements 1 and 2, and then secondly we took the linear interpolation functions for the solution, u as u1 times 1 minus h by l plus u2 h by l, and then next step is we are writing the Brownian differential equation in the weight form by multiplying it with the weight function, and then using UV rule to make it weight form, and then finally we have just substituted the all the equations into the integrals and then solved it to get the stiffness matrices in this format. So let's just solve it for here. K11 here is 0 to L E times 1 by 4 1 plus x 1 by L square dx. Here our domain was in this way. First element, second element, we are taking for the first element, and the whole part is 2 meters. So for the element 1, x is 0 and x is 1 for the first element. So it's just 0 to 1 e times 1 by 4 1 plus x 1 by L square dx. It's and L in this case is 1. So e times 1 by 4 times integral of 1 plus x is x plus x square by 2 with 0 to 1 limits. E by 4 times 1 plus 1 by 2, 2 plus 1 3, 3 by 8 times e. So this is your K11. If you notice here it's K2, 2 is just minus 1 by L square. Like every term is same, just the coefficient is negative. So it's just K22 will be minus 3 by 8e, and K21 and K12 are similar. Exactly same terms are present. So this is K12. K21 is minus 3 by 8e, and K22 is same as K11. So K22 is 3 by 8e. And then so for the first element, our equations will be e by 8, 3 minus 3 minus 3, 3 times u1 u2 is equals to f1 and f2. This is for the element 1. Then similarly we need to do everything for the second element. In this test we will take the weak form and then start from here. This is our weak form. Here we need to be careful for element 2. Our element 2 starts at x is equals to 1 meter to x is equals to 2 meter. And if we are choosing the local coordinate system, it will be from 0 to L. So while considering these things, in element 1 it's fine, it was element was from 0 to 1 and even local coordinate system is from 0 to L, so it was simple. But in this case we need to be careful. Okay. Let's do one thing. We use maybe, let's say, another zeta for local coordinate system and it's for the global coordinate system, just to avoid confusion between these two. So here we have E, and A is a function of global coordinate system, and here we have U as U1 psi of, like, local coordinate system plus U2 psi of psi 2, and psi 1 of zeta is 1 minus zeta by L. Psi 2 of zeta is zeta by L. Fine. Uh, just remember that here it's these are in the function of local coordinate system. Okay, and this element limits are from not 0 to L. Sorry, this is from 1 to 2. So before proceeding further, we need to, as you observe that these two are in zeta and this one and integral is in x. So we need to make everything into one variable, then only we can solve the system properly, solve the integral properly. For now, so let's see how can we do that. When x is equals to 1, zeta is equals to 0, and x is equals to 2, zeta is equals to L. Fine. Then we can use this relation x is equals to 1 plus zeta by L. You can see that from these relations we can find the relation between x and zeta. So when x is 1, zeta is 0, and when x is 2, zeta is L. So, like, if you substitute zeta 0, x is 1. If you substitute zeta L, x is 2. Then you can use this conversion. Then we need to convert a of x in terms of zeta. We have a of x is 1 by 4 times 1 plus x, which is in terms of zeta it would be 1 plus zeta by L. So 1 by 4 times 2 plus zeta by L. So now you have the area as a function of zeta, and then you need to convert the integral dx. So you have x is this one, so dx will be 1 by L d zeta. Now you can convert everything in terms of zeta. So your weak form for element 2 will be here E a of zeta is 1 by 4 times 2 plus zeta by L, and du by dx is u1 times minus 1 by L plus u2 times 1 by L. Uh, for w is equals to psi 1, which is minus 1 by L dx is equals to, we will just write this as maybe q1, and this is not dx, we want to convert into d zeta, which is nothing but 1 by L d theta, and the limits are from 0 to L. So now you have a whole system in terms of zeta, then you can proceed to solve it. So this will be, and again L in this case is just 1 meter, length of the element is 1 meter, so L will be 1 meter. So we can write 0 to 1 E times 1 by 4 2 plus zeta by L minus 1 by L times minus 1 by L. It's nothing but minus times minus plus 1 by L square d zeta, and then there's 1 by L here, L cube u1 plus 0 to 1, similarly E 1 by 4 times 2 plus zeta by L 1 by minus 1 by L cube d zeta u2 is equals to q1. So this is for the w is equals to psi 1. This is the corresponding equation, and then we will solve this. Okay. Similarly, for w is equals to psi 2, it would, if you solve it, it would look like e times 1 by 4 symmetrically. So this is how you will get for w is equals to psi 2 equation, and similarly for that this will be k11, k12, k21, k22. Remember that this is for the second element. Don't confuse this case with the first element case. So for second element, this one is your equation. Okay, maybe we will just use u1 and u2. We'll keep two superscript to just to show that it belongs to the second element. Let's solve for k11. It would be 0 to 1 e times 1 by 4 2 plus zeta by L minus 1 by L cube d zeta. Here zeta L is 1, e by 4 2 zeta plus zeta square 0 to 1 times minus, sorry, it's plus 1. So e by 4 times 2 plus 1 minus 0. Two plus 1, 3. This is what you will get. Is it clear till here? Hmm. One second. 1 minute. Sorry. Oh, sorry. I think here zeta square by 2. I just made a small mistake. It should be, yeah. Now it looks fine. So similarly, K22 would be minus 5 by 4e. K sorry K12. K21 will be minus 5 by 4e. K22 will be 5 by 4e. So your equation would look like e by 4, 5 minus 5 minus 5, 5 times u1 2, u2 2, q1 q2. This is for the second element, and you have equation for first element, which is this term. This is your equation for first term, and these are like u11 u1 u21. Is there any doubt still here? I hope everything is clear. So once you have this elemental stiffness matrix, next step is you want to do the assembly. For that, before doing for assembly, you can yes, Shiva.
Uh, it's a
Yes.
little basic doubt. Uh,
Yeah.
actually, about I'm not sure about this conversion from global and local. Actually, we can't change directly the limits. Is it fine? Like instead of using
Uh,
0 to 1, and for the next element, use 1 to 2.
uh, you can you can directly use 1 to 2, Then the issue is you cannot use this shape functions. The other way around is when if you let's say you want to keep everything, you don't want to do any kind of conversion, let's say, then there is an alternate way where you can directly start with the element as x is 1 and x is 2, but here shape functions would change. You cannot take 1 minus x by l and x by l here. Here it shape functions would be a bit different. We'll see how the shape functions will look like if we take from x is equal to 1 and x is equal to 2. This is at x is equal to 1, u is u1, at x is equal to 2, u is u2. And like we already saw, we are taking linear shape functions a plus bx. So if you substitute x is 1, you have a plus b is equals to u1. Fine. At x is equals to 2, you have a plus 2b is equals to u2. Then you will have b as u2 minus u1 and a as u2 minus u1 2u1 minus u2. Are you following this one?
Yes.
Uh, and if you write u is equals to a is nothing but 2u1 minus u2 times plus b is u2 minus u1 times of x. So you will have u1 times 2 minus x plus u2 times minus 1 plus x. So you need to use these functions. If you use this function, then you can directly use this as a shape functions, substitute them in this function, then you don't have to convert the integral. You get it? It's either way around. Like right now, like if you want to use these local shape functions which are standard 1 minus x by l and x by l, then you have to convert the integral in terms of local coordinate system. If you don't want to convert the integral into local coordinate system, you can just find out what the shape functions for this element in global coordinate system will be. In this case, it's 2 minus x and x minus 1. Fine. You can use this directly. You can substitute this one, like psi 1 will be 2 minus x and psi 2 will be x minus 1. You can proceed with this, substitute them in this equation, and then directly solve everything in terms of x. You will end up with same stiffness matrices in both the cases.
Here, U1 and U2 have superscript of 2, right?
Yes,
U1,
yes.
2.
Yeah, true. These are,
Yeah.
they have superscript 2, like belongs to second element.
Okay, okay. Understood.
So it's clear. No. It's just that we want you need to be very careful when you are using the local like standard shape functions. Those are in a different coordinate system 0 to l. It's like as I said, the global one is x, which is starting from 1 meter to 2 meter, but your local is starting from 0 to l. Just to remove the confusion, like be clear, we are using zeta here, and you need to notice that we are writing u in terms of zeta and w in terms of zeta, but the area which is a function of x is still in function of x, and the integral is also on dx. So before solving the integral, all the functions should be in the same variable. So here I went forward to converting x to zeta. You can do the other way around as well. You will end up with the same final form. So once you have this two element stiffness matrices, you just need to one thing you have to notice, that is first, second, third node, nothing but at the second node both u2 second element first degree of freedom and u first element second both are same. You can use the global degree of freedom something like u1 u2 u3 as well. We will use this and then we will proceed. So if you are writing in u1 u2 u3, then k will be, just take e common outside. So for this is u1 and u2, this is u2 and u3. u1 and u2, it's 3 by 8, 3 by 8 minus 3 by 8, 3 by 8. It's like corresponding to u1, corresponding to u2. There is nothing related to u3, so this will be zeros. Similarly for this is u2 and u3. So corresponding to u2, you need to add plus 5 by 8, u3 minus 5 by 8, minus 5 by 8, 5 by 8, corresponding to u2 and u3, and you don't have anything related to u1 there, so it will be 0. And this one will be f1, f2, and you have q1, f2 plus q1 and q2, and these two will get cancelled out. You can think them as an internal force. It's something like if you take one element f2, first element f2 is acting like this, and in second element q1 is acting like this, and they both cancel out. You can think it in that manner. So this is your case, and this is node 1, node 2, node 3, and F1 will be your applied force, which is P is 5 kilonewton. So like, well, so till now you have, it's fine. Next step is to apply the boundary conditions before solving it. Unless you apply boundary conditions, you cannot invert this matrix. It will be singular and inverse doesn't exist for this matrix. So let us apply boundary condition. Here F1, which is you can see EA du by dx, this term. This is nothing but the force acting on the uh, node number 1, which is we calculated initially as 5 kilonewton. Yeah, P is 5 kilonewton. This will be the F1. So F1 is 5. This one is 0. We don't know what is Q2 because it's just fixed. We know that the bottom is fixed. We don't know. Here Q2 will be the reaction force. So if we take it as a free body diagram, then we will have some reaction force at the bottom, right? That is nothing but Q2. And you know that at the bottom it is fixed. It means U3 is 0, and we don't know what is U1 and U2. So sorry, it's not 5 by 8, it's 5 by 4. Wait, answer in 5 by 4 or 5 by 8? Sorry, it's 5 by 8. 2 to 4 and 8. I'm sorry, everything is in terms of 8. Our work became easy. Yeah. So 5 plus 3 is 8 by 8 minus 5 by 8 minus 5 by 8, 5 by 8. Okay. So now you have applied the boundary conditions. You can solve this system of equations right now. Now we will just for the sake of simplicity, let's just take E as 1. Then we will have these equations. 3 by 8 u1 minus 3 by 8 u2 is equals to 5, and in this case minus 3 by 8 u1 plus u2 is equals to 0. Two equations and two unknowns. It's just, you can just add them. 1 minus 3 by 8 is 5 by 8. u2 is equals to 5. u2 is 1 by 8. And u1 will be, you substitute u2 in this, and minus 3 by 8 u1 is minus 1 by 8, and plus u1 is 1 by 3. So this is your solution. u1 is 1 by 3, u2 is 1 by 8, u3 is 0. So these are the nodal solutions. So you want to find u as a function of x. You want to know how the u will look like, right? So if you are this is two elements, and these are your nodal shape functions. Now we know these values as well. Now finally we want to know how u of x will look like. It's 1/3, 1/8, 0. So right now we again go back to the shape functions, how they will be, and then write it. So from x0 to 1, u of x will be u1 1 minus x by l plus u2 x by l. L is 1 here. Okay. Which is nothing but u1 is 1 by 3 times 1 minus x plus u2 is 1 by 8 times x. So 1 by 3, 1 minus 8 by 8 minus 1 by 3 times x. So this is your u of x between 0 to between x and 0 and 1. For 1 and 2, your u of x will be u2 times shape functions, u3 times shape functions. Here we can use the ones which we derived, 2 minus x and x minus 1. 2 minus x, x minus 1. 1 by 8 times 2 minus x. So your final solution is u of x 1 by 3 minus 5 by 24x 1 by 8 times 2 minus x. It is from 0 to 1. It is from 1 to 2. So this is your FEM solution. This is how you get the final solution. Any doubts regarding the method? Any like any kind of doubts is fine. One more thing. Here we are. Once we get this equation, here we are solving by hand. That's why I directly multiplied it and uh, solved it directly. But in general you will have much more elements than to maybe 10, 100,000 elements, and obviously you want to code it and then solve it. In those cases, like we want to, we cannot multiply it. So in those cases we find inverse and then solve it. So it's like wherever the zero is present, these zeros columns we remove it, and then remaining elements, maybe something like small, like after applied boundary condition, whatever the remaining unknowns are there, we solve for them. Right now with this K it can be inverted. So this is how we do when you do programming. So first you apply boundary conditions, then you remove the things, and then remaining sub matrix, stiffness matrix, you take it, you invert it, and then you get the solution. Any doubts? I'll just repeat briefly repeat whatever this problem I have solved. So our initial problem is a bar, which is vertical bar with varying cross sectional area. On the top we have a distributed load of 20 kilonewton. uh, so this is our problem, and we know the bar Downman differential equations. So we want to simplify it into a 1D problem. So we made it as a 1D bar, and we know we need to keep in mind that area is a function of x, that it changes with length, and distributed load is 20 kilonewton. So in 1D it will become a concentrated load, which is nothing but the area times the distributed load, which is 5 kilonewtons in this case. Now we have the whole domain, and then bottom boundary condition is u is equal to 0. So we have the governing differential equation, we have the domain ready, and also the boundary conditions. Once we have these three things ready, we can proceed for the FEM procedure. We need to discretize the domain. In this case, I am just going for two elements, 1 and 2. Then and both are of equal size, 0 to 1 and 1 and 2. Then we need to choose the interpolation functions. I went for the linear interpolation functions, uh, which will be in this way for the generalized element 0 to L. And then but if we want to use other like global coordinate system, then accordingly you need to set this modify these shape functions. Then we have start the differential equation. We want to convert into integral equation. In order to do that, we take the error, which is these equations, multiply it with a weight function, and then integrate it to the whole domain is equal to 0. Sorry, we are doing it for one element, then we will repeat this process for the second element as well. So once we have the integral form, then we want to use the UV integration rule to reduce the order of derivative, such that we can use lower order interpolation functions. So when we do the UV rule, we end up with this boundary terms, which allows us to substitute the boundary conditions in the later part. Then we directly substitute uh, the solution, like assumption u, the interpolation part, whatever we have assumed, into the equation. And for the weight part, we need to assume like two cases, psi1 and psi2. For weight psi1 we will get one equation, and for psi2 we will get another equation. From these two equations, if you simplify and modify, you can write them in terms of Ku is equal to F matrix. And this one will be the for the first element. Similarly, for the second element, you need to repeat the whole procedure. Just you need to keep in mind the coordinate system which we are using. Like if you want to use the standard shape